right. So first of all, last time, I think now like everybody did the work already. So I think it should be clear about like say the remaining question last time about like how many draws you're taking and all that. But let's just take a few minutes to go through that. So we're all in the same picture. But I think since you did all of the generation stuff, I'm sure you are fine. Let's just do get it straight here. I think it was this, right? It was this slide-ish. Yeah. So last time we ended here, and we're talking about, well, how can I generate a synthetic value for each observation, and we do that for all of the observations. So that's why here I think we highlighted like one set of posterior draws that's talking about beta 0, beta 1, and sigma, right? When we're doing simple linear regression, and then I included this function called synthesize that takes x, which is the unsynthesized variable here, right? And then the index. So you can have different ways of like writing it. I just trying to make sure that we can later decide which of the 5,000 that we're using. So I put an index here, and then n is the number of observations that we're doing. Okay, so then in order to do a posterior prediction, you first of all get the mu's, right? The mu I. In this case, you can get the index. So if it's 1, then you're taking that first set of draws out of the 5,000, and I'm taking beta 0 plus x times beta 1. So I can get a mu I, because that's the linear combination, right? Beta 0 plus beta 1 times x. And then we can do a synthetic y using our norm function by the mean that we did, the mu, and then using the sigma that you have from the same iteration, okay? And then we do this everything by a vector instead of doing like a loop for each observation, because you can operate by vector. So in the end, the input x is a vector of the unsynthesized variables, and then the index is which set you're using. Yes, Sarah.
Is this meant to match what we're doing up, like one slide before?
What was one slide?
I was
oh yeah.
confused just because it looks like here we're generating one value for expected y instead of n values.
Right. Yeah.
And then generating from that like n.
Right. So
I don't know if that's the same.
Sure. Okay. So let me just using this slide. So one set of posterior draws. So we're talking about one iteration, right? So you have one draw for beta 0, one draw for beta 1, and one for sigma. Okay.
Right. But are we doing n x's or just one x?
Yeah. Right. So if we break the task like into the tiniest step, it's for a particular, say, y1, right? We're doing like, say, in order to get the mu1, a draw for that, you use beta 0 plus beta 1 times your x1 value. And then the second step, to do a prediction, you do a normal, right? So that's for each one. So here, this slide is showing like the entire process. We need to do it for every observation. So the script that I included here is doing that for all observations, or I should say whatever that you supply for x, that would determine how many observations you're doing. So I'm imagining that you can just input the entire vector, I think. Yeah, the vector of the log expenditure. So that's what I'm saying. Say here, this is, so you notice that I didn't use the index of I because I'm doing it for the entire data set. Meaning that, right, so the key here is that this is still, so if my index is 1, let's just say it's 1, I'm using the first MCMC iteration for the draw. So this post bracket index and then beta 0, that's a scalar, because that's the value for beta 0, right? And this is the scalar beta 1. This is scalar for beta 0 at that iteration. So this x, so the dimension of this x determines, I guess, how many you're doing. If you're giving it as a vector of length n, which is like the value of xi for each observation, then this mean y is going to be a vector of length n as well, right? And then this one will also be length n, because you see that here, n is the number of observations, and then the R norm can be applied to a vector. So this is a vector, this is a scalar.
Oh, okay.
Yeah. So I think at least you can tell me otherwise, because you have done all of that, and we're going to go back to the results that you have. So when I wrote this, I was thinking that we are generating the syntactic value, syntactic y for each observation in one code, in one line of code.
Because I was running it, and it could be just the way I ran it. I was getting the same value. So I compiled all the values that I was putting in for
so that's your x, right?
And it was just running it on one
observation.
But it could also be just the way I was inputting it.
Yeah,
like,
maybe.
I don't think I was inputting it.
Okay,
right.
I see. How about everybody else? Like when you run, like, so I guess first of all, like I think are we on the same page about what this function is doing? Like, so what I'm thinking is this function is trying to take in an x. It could be, in this case, as a vector. If you're just doing a the log expenditure. This is the variable that is not sensitive, so you do not synthesize it, but then it is the predictor variable. So you use that for your prediction. And so if you're set index to whatever value that you have, if it's a scalar, then you will just take one row of that post output, and that will give you a value for beta 0, value for beta 1, and value for sigma. And then, so it really, so x, so if you like say, we haven't talked about this yet, but there are many different flavors of synthetic data, like say how many you want to synthesize. In this case, we are having log expenditure, right? Which is not synthesized, but we use it as a predictor. The other one is log income, which we think is sensitive, so we synthesize it, right? So the output will be what we call x, and then comma, I guess, y tilde here. And then you can think of it as a matrix, right? When you have all of that. So for this case, if you have variables that are not synthesized, and then you also have variables that are synthesized, we call it as partial synthetic data. We have a slide at the end, but I can just mention this here. Partial synthetic data. What we mean by that is not every variable is synthesized, because only maybe one variable is deemed sensitive. And if you want, you can even do like partial synthesis in a way that I don't synthesize the y for every observation, because maybe I only synthesize them, I don't know, is log income, right? So maybe I think like the larger ones are sensitive. So maybe I set a threshold. Everything above that I synthesize, everything below it I don't synthesize. In a sense that your output will be x, y tilde, but that tilde, I mean, it is y tilde for not all of the observations, right? So in that case, it's still partial synthesis. So the reason why I mentioned this is because the way that I wrote the function in the first place, you might have other ways to do it. It's totally open-ended. But I was hoping to use this x in a flexible way, that if I want the entire record, the entire data set, every observation to have a synthesized y, then I just input the entire x. But if I only wanted to half of it, whichever the half, I don't know, but you can, or like 30% of them, 50% of them, 80% of them, then you can be a little bit more flexible. But you can have other ways to write the function. So I can check, like we can check what you have afterwards, but I would imagine if you supply a vector of x to be the unsynthesized variable, the output of this, right, should just be x, which is unsynthesized, log expenditure, and then the synthesized log income. Okay. All right, and then I think we have, right, so I gave a demo. If index is 1, we're using the first of the 5,000 sets, and n is the number of observations. So you can use this to do it. And you notice that I named the data frame to be synthetic_1. And then later I changed the name of the column just in case later if you want to plot it, especially using ggplot too. And but you can do other naming convention, or even if you don't name it, I think you should be fine. And last time, really briefly, I touched upon this. Typical practice actually generates multiple sets of synthetic data. Later on, we're going to learn why we want to do it. The short answer is, if you only do one, you are not capturing enough uncertainty in the model that you introduced. Okay. So typical like practice, for example, you can do 20 of them. And in that case, so basically, I wrote in the way that I did it. I wrote, I think, yeah, I assign M to be 20, and then I create a vector. I create a vector of list. So I'm trying to use. So this is the how you can use the list. Use like bracket, and then the index will give you like the index of the list, which of the list that you're working with. So I have. So if I set M to be 20, I have a list of 20 data frames, and each one is a synthetic from a particular iteration. And the way that I'm writing it, just so you know, oh yeah. So I think I was trying to use the last 20. So this again goes back to the previous question last time. We do have 5,000 iterations, but you only need, in practice, 20 synthetic data sets. So in practice, you only use 20 of them. Whichever 20 is fine, because by this point, it has converged. The chain has converged, so it should be fine. And also remember the thinning that we did. I think we did thinning of 50. So meaning that after like any of the sample, the adjacent sample should be independent from each other. So when we're doing, so actually one thing I should mention is when you're generating multiple synthetic data sets, we want to generate from like independent MCMC iterations. But because of the thinning that we did, so I think any of the 5,000 should be fine, so I picked the last 20. And that's why I wrote this, is that when L takes value of 20, you will go up to 5,000. But you can pick any 5,000, any of the 5,000. And I think just to go back to this point really quick, yeah, it was a little bit confusing, I guess, at the beginning. Like, oh, why do we have 5,000 in the first place, but we only use 20? Or for the demo, we only use one of them. What's the point? So first of all, for synthetic data sets, like we said earlier, we typically generate multiple of them. Okay, we're gonna go into detail why later, but just take that for sure for now. And so we do 20, and then the reason why we have 5,000, I guess in this case, is not so much for generating synthetic data, it's for like all of the MCMC diagnostics and all that. So that's why we have 5,000 to start with. But you're only gonna use maybe one of them, or maybe 20 of them, or if you want, use 5,000 of them if you want. Okay, but that's why there is this discrepancy between these two numbers. And I think that was why it was a little bit confusing last time. Okay, so I think that part is fine now. So if you use some version of this script, I think you should be able to get 20 synthetic data sets. So in each of the synthetic data set, we know that it contains the unsynthesized variable, the x, and then also the synthesized. So I add I rename it with the underscore and syn from it. So like a way to double check that your work is fine, whenever you're accessing one of the lists here, you should be able to see like the x-axis, or sorry, not x-axis, it should be the first column, which is the log expenditure should be identical because you never change them, right? And then the second column, in this case, the log income syn, should be different. They might be identical, maybe some records, but shouldn't be all of them. Okay. Yeah, so this is the mechanics, and I think I've asked you to do the work using your own code. So I think this might be a good time now for me to come to. Yeah, so I have to, let's see, let me share. Okay, my Chrome. So right, so it was the first part here. We just talked about it. Okay, so make sure that we know like we're using a particular iteration, and then we use 20 and 5,000. That's their relationship. Okay, and okay, so what I was hoping to spend time on is part of pretty much the entire section 2 here, because I was asking you to so in class we did the demo in the slides. We did the demo of the simple linear regression just to start easy. But you might have other regression models that you want to use. So I was asking that each of you to produce one synthetic data set for the CE sample. And at the end of the day, you can try to see how good your model is by doing some visualization. So that's what this questions are about. For example, how about like with the synthesized log income against the original log income, like what do you find? Okay, so this is sort of, it's going to be a scatter plot. So we're going to like take a sample of what you have done in a minute and then see how things are doing. The second one, compare the mean and median of the log income in the original data set and the confidential data set. So this is one way to check the utility. We talked about utility in a sense that, well, when I have my synthetic data, I would love to have my inference results to be very similar to if I can have access to the original confidential data and see some of the inference outputs. So mean and median typically done for numerical variables. So that was what I was asking. And the last one is compare the point estimate of the regression coefficients of log income and log expenditure in the two data set and check are they close to each other. So this again is a way to check utility. Okay, so this is just one of the A regression analysis that you can do. And yeah, so this is the big picture. So let me go to, let's see, I think I opened you here. Let me just double check. All right, yeah. All right, so I'm just going to start one by one. So I guess I start with Eric. So do you mind telling us, I might just maybe just jump to the point where you do the comparison.
Yeah.
Yeah, so yeah, you can start. I will just scroll here.
Yeah, just starting from the beginning. So I decided to take what we learned from the class about the simple linear regression and use a multiple linear regression with urban, rural, race, expenditure for the synthesized income variable. And so let's see. Should I just explain maybe like this?
Yeah, we can probably just assume the model is fine.
Okay.
Yeah. So basically, Henrik is doing a multiple linear regression using all of the predictors, but I guess you're only synthesizing the income,
Just
right?
income,
Everything
yeah.
else the same.
Yeah.
Okay. So you do have multiple parameters here. You check the diagnostics.
I just checked one just for beta 1. And for the synthesis portion, I had a little bit of trouble that actually Kevin was able to help me with. But what we ended up doing was creating like for like the code. Yeah, for just like the little like the code above. We created a new data frame for each variable that we use for like the synthesized function. And from there we were able to gain an output of like the synthesis log income. And what was found from like from the scatter plot of synthesized log income against the original log income, we can see like a linear positive linear relationship. I wasn't sure exactly if that was like what we expected, but you can tell that like the relationship is very similar, but the mean and median are about like 2 units off. You can see that the median. So
the means are close.
Yes, of the synthesized income is approximately around 8, while the original log income is close to 10. And so we can see that in terms of utility, we keep like the trends the same, but for the disclosure risks, we aren't displaying the exact same numbers as the original log income.
And let me just also maybe check the regression coefficient. If you, let's see. Oh, I see. So I guess you plot them.
Oh yeah.
Okay. Yeah. No, that's fine. Yeah. All right. So maybe let's see. Let's maybe state. So first of all, I think so. Henrik was talking about some complexity here. I think it was mostly probably because the different types of predictors, and then you have to get it right, I guess, when you're doing the predictions, right? So that's why you initialize, I guess. I mean, you have to create new dummy variables in some sense, and then get the correct beta, and yeah, all of the different betas in the right place. Okay. Yeah, so that I understand. I think we probably just all need to be a little bit careful. What I want to maybe focus on a little bit here, since we're on this plot, is so what do you think? Why I asked you in the first place to plot the I guess original income against the synthetic income, or vice versa, whichever. So like we have an output from Henrik's result, and what do you think this kind of plot is telling us, or why do we care about this plot? Or maybe I should be plotting something else. That's my first question. And maybe we can just pause here so you can chat with your neighbor to see if we have similar ideas here. Why do we want to, why do we want to have a plot like this, and whether, like what this plot is telling us in terms of, I guess, utility, or maybe also risk. I mean, it's not an evaluation. It's not actually the evaluation of like a metric, but what does this tell us? What do you think? All right, so let's hear from some of you. Yeah, this plot again is the y-axis is the original, and the x-axis is the synthetic. And what does this plot tell us? Maybe you can comment from the utility perspective, and as well as the risk perspective. I mean, I know we haven't evaluated anything about the risks yet, but okay, let's talk about utility first. Anybody? What do you think this is telling us? Or can we get some sense of how good the synthesizer is doing, given this plot? Right?
I think it sort of shows the density, the distribution of the two data sets, like the density of data points at like each level. If they're similar, it shows that the synthesized data set and the original data set have similar distributions.
Yeah, good point. So I'm glad that Ray mentioned the density. So the scatter plot obviously is not giving us the density plot, right? So what we could do, I guess I didn't ask about it, and so nobody did it, but what we could do is maybe do a density plot, a two density plot. I mean, one for the original, the other one for the synthetic, and then do it like one over the other one. Okay. Right. Is there a way I can show this? Yeah. Anyway, so Sarah has one here, like showing us, in a sense that you can plot the density plot like on the same plot, and you can see how close they are. Okay. Yeah. So that would be definitely like a more direct way to compare, like say how good the utility is in terms of like preserving the overall density distribution. And I should also mention like the comparing the mean values as well as the median values are sort of doing that as well. Okay. All right, so, but I think also earlier some of you were talking in the discussion that overall you see a positive trend, right? Like there's some like moving around like of the records, which is good because we want them, because then that is giving us the privacy protection, right? But overall we do see like original log income and the synthetic log income are positively correlated and all that. Like you can think about, yes, in some way it should be preserving the relationship to those. So, okay, so from the utility perspective, I guess we get a sense. What about from the risk perspective? And I should just mention maybe let's compare two data points here. Let's maybe compare this one. Just remember this one. The largest one on the synthetic log income, okay? And maybe this one, this two. Okay, you see this one? And this one, okay? So what do you think? Like, spend some time, think about it, and talk to your neighbor. Like, so for these two records, what do you think the synthesizer has done to them from a risk perspective? Okay. So again, we haven't talked too much about for the risk for continuous data, right? Last time we talked a little about it. For categorical variable or categorical outcome variables, what you can do is you can look at exact matching and see whether it is a match or not. Okay. But my question here for you is, well, what if we have continuous outcome here? it's univariate, so at least we just have one dimension to worry about. So what do you think in terms of, like say for these two records? Do you think their risk is going to be dramatically reduced by the synthesizer? And if so, why? If not, why? Or you can also think about among all of the data points here, which ones you think might have the highest protection? And which ones you think might have the lowest protection? So if you're not too sure like how to think about protection, we can spend the time on that as well. But for now, maybe just like brainstorm with your neighbors to see what you think. And I'm gonna stop sharing here.
It's closer to the mean or the
It might be pulled in a little bit.
All right. So
The synthetic is.
yeah, since Sarah's has two kinds of plots, so let's use hers. I mean, it's probably a different. Did you use the same model or like similar?
It's the same model.
Okay,
I think
alright.
this is just standardized.
Okay. Yeah. Okay. Sounds good. Yeah. So we get I mean, the modeling perspective. I mean, today we're gonna talk different models as well, like say what you need to care about. But for this discussion, I want you I want you to get a sense of what the synthesizer is actually doing to the data. Okay. So one thing we noticed, especially Sarah has it here. I didn't ask for it, but this is great because when you're doing like two density plots, I mean, one is the synthetic log income, the other one is the original. And if you do it like on top of each other, you can sort of see how good the synthesizer is preserving the overall distributional characteristics. Okay. And of course, you can try to compute other things like the mean and medians or other kind of stuff. The closer they are, the better the synthesizer is preserving the distributional characteristics, meaning higher utility. Okay? So of course, you can probably even improve that a little more if you want, but at least this kind of plotting can give us a sense of how good it is doing. Okay. But if we are doing this, which is what I was asking you to think about, you can realize that. So again, for each dot, at the x-axis the synthetic, right? The y-axis the original, and we know that they're unsynthesized predictor. Let's say if it's just the log expenditure is the same, right? It's the same data point. I mean, it's the same. One is for the every record has the same. Sorry, I should say each record will have a fixed unsynthesized log expenditure, right? But then for the original, you have a value for the original log income. Standardized for the synthetic one, you have another one. So this plot is trying to show you, like say, by doing synthesis, how much moving around of the log income, standardized in this case, that you have done to each record. Okay, so for example, this one, its original, once it's standardized, I guess it was maybe -1.8, right, for the original value. But then you got like moved a lot in some sense, because on the x-axis you see that the standardized synthetic log income is close to what, 3, right? So that record sort of like got moved to a little bit more extreme after you do the synthesis, right? Let's see another one. Maybe this one. This one looks a lot of like a bit extreme, but maybe didn't get moved that much because on both x-axis and y-axis, this value is a bit extreme, right? So on the y-axis is close to 2. So before synthesis, it was already extreme. Yeah, but not the extremist because you can see even greater values than that. But then the synthesizer got it more extreme because on the x-axis, you move it further away from the cloud of the data points. Right? So can you see any values, I mean, roughly which ones you think actually were not so much affected by the synthesizer? Which values or?
This one on 2, 2.
Mm-hmm. Yeah, those ones on, I guess, like 2, 2. So pretty much if you're drawing like a 45-degree line, y equals to x, any value, so it's hard for me to draw. If I'm on there, I can do one, but imagining going through, like, so this is 2, 2 here, right? So you have 2, 2, and it's 0, 0 here, right? So just get a line going through here. So any record close to that line, or even just right on that line, tells us that we haven't changed much to those records, okay? we will have to determine later, like whether those records will be protected more or less. Because earlier, I mean, I just overheard what Henrik was saying in the discussion, like you also need to see how close one record is to the other records. Because at the end of the day, when we're trying to do identification disclosure risk, we're trying to find out how many records are similar to this record, right? Maybe it was very special in the original data, but after the synthesis, it got into a big cloud and it has a lot of records around it, then maybe it's not that unique. So you're gonna reduce the disclosure risks. Okay? But what I'm trying to tell you all at this moment is you can see that the synthesizer did a lot to pretty much every record. Only a few probably are very close, it's hard to tell, but like on that y equals to x line, not gonna be many. Yeah, but if you go through just this line, you can see all of those records up here. These are the records who started off with high original log income, right? Standardized. But once you do the synthesis, they become smaller because they are in this part of this graph. Okay? And if you do all of those records here, then these records are the ones who started off with maybe medium-sized original log income, and maybe get a little bit larger along the way. Okay. So what I want to show you is, well, if you look at record by record, you will see the synthesizer has been moving around all of the records a lot. And I should mention, later we'll see that it is exactly because of this moving around, you're giving protection to this record. Okay? And the moving around probably has not been too bad in terms of utility, because if I don't look at the utility at the record level, because at the record level scatter plot, you can see that everything was changed, right? If you think about, oh, that's not good. However, if you go to density plots like this, it's not perfect, but it's not bad, in a sense that marginally, the log income in the original data set and the log income in the synthetic data set, I mean, distributional wise, they're not that different from each other. And earlier, I mean, Henrik has shown the mean and medians are not that far from each other either. And so anybody did a regression analysis? Like show, I mean, because it was the last part of the question that I had. I just wonder if anybody did it, we can go to your output. Because I was wondering if you did a regression, I guess, log income on log expenditure and look at the output to see how close they are. Yeah,
Yes.
yeah, okay, let me. Okay, I didn't open. Is it at the bottom? Okay.
Is that what you're saying?
Oh, yeah, okay. Right, okay. So, right, so this is a way to check if so did you use a multiple linear regression or something? Okay, yeah, but at the end of the day, you have the synthetic log income, right? And then we're trying to do the synthetic log income doing a linear model, simple linear regression of log expenditure over log, given log income. And then, so that's in the original.
Yes, that's the original. And
That's
you
the
go to
original.
ST, it's just the regular. I just grabbed you right away.
Right, okay, yeah, that's fine. So, okay, so what I was asking is, yeah, probably just look at like the intercept and the, let's see, coefficients for the, oh, okay, that's the intercept, that's the slope, right? Mm-hmm. Yeah, so do you think they're close? I mean, what we're trying to get is, well, even though the records have been moved around, but some kind of analysis that you can do with the entire file might not have changed much, and that's what we care about utility, okay? And it's indeed this moving around. Later, we're gonna see that it is providing us privacy protection, but we have to go into the detail how to evaluate, so we don't know now. At least we get a sense. Some of the records have moved a lot. Some of them are like staying around what they used to be. And but another point Henrik mentioned as well, how unique or how isolated one record is going to be determining how risky it's going to be afterwards. So we're gonna go into that, I think, maybe a couple of weeks later. At least we get a sense. So, so this regression analysis can tell you like how close they are. A lot of times we will return, so I didn't mention this, so I'm sure you didn't do it, which is totally fine, but a lot of times you can provide confidence intervals for those parameter estimations, and then we can see how much overlap those can be. So that will be a more, I mean, because again, this is one run, and we don't know how uncertain each of the estimates are, but down the road, I mean, next time we're going to talk about how you can do different ways of evaluating the utility, and those will be the ones that we're going to cover. Okay, make sense? Sense? Yeah. So the key story here is, well, first of all, we need to know how to do that. So hopefully everybody did it correctly. And then when you do the scatter plot can tell you how much each record is being moved around. But if you want to check utility, you can do what we did, like number 2 and number 3 here, or do what Sarah did, like doing the density plot, one on top of the other, and then see how close they are. So you can actually return certain metrics between two different distributions to see how close they are. So we're going to cover those next time when we talk about how to evaluate utility, at least to get a sense of different things you can do. Okay, but I do want to emphasize that the scatter plot is helping us to understand what the synthesizer is doing. Okay, and it is doing, I mean, we now know how to make the synthetic data, so you know we actually apply the model, right? And then from the model we make predictions, and we use those predictions of the y's, which becomes the y tilde that we've been using, that they will be the synthetic value. So those are the ones that we actually find and release. But it's because of the uncertainty that we have the parameter estimations, so beta 0, beta 1, and sigma, right? And also making prediction. You're doing the R norm. So that's how all of those uncertainties being done to this to the model itself, in a sense that the synthetic data that you generate does encompass all of the other things that you have done. Okay, so keep in mind that typically whenever you're trying to plot, like say synthetic value, especially for numerical variable like this, continuous variable like this, when you do a plot, I mean, it's very unlikely to be like y equals x. Otherwise, then like what Sarah was saying, well, if you do that, you didn't add any noise, you didn't really synthesize anything, everything was just, it's all points. Whereas you will see synthesizer, like a simple one that we can come up with, already moves around a lot, but then utility-wise, it's utility-wise, it's because utility, especially a lot of times we talk about it, is at the file level. It's not for one particular record. Okay, we're looking at like say density, or like when you do regression analysis, you're looking at the relationship between two variables. And then even though each record can be moved around a lot, distributional-wise, it's fine. It's fine in the sense that the utility could still be very high. And that's the balance that we're trying to strike. Okay, okay, all right, sounds good. So the last thing from this is, I think, yeah, so right, so the last thing, I put a couple of small topics in this slide. So